Alright, so hello and welcome back. Have another problem to solve here. This is in reference to another LeetCode question, a LeetCode problem. And this problem is, let me actually get the problem up. Just give me a moment. This is an interesting problem, but it's, I actually solved this one too already. We'll go through it. So this is it's kind of an unusual problem. This is very atypical kind of a thing, but we'll get into it. We'll get into it if once it loads. So I'll read the question first. I'll start with that. So generate random point in a circle. Given the radius and the position of the center of a circle, implement the function random point, which generates a uniform random point inside the circle. Implement the solution class, solution double radius x center, double y center. Initializes the object with the radius of the circle radius and the position of the center, x center, y center. Rand point returns a random point inside the circle. A point on the circumference of the circle is considered to be in the circle. The answer is returned as an array x, y. Okay, so you get solution, rand point, rand point, rand point. And so there's a x, y, and a radius, x and y, 3 points, and you get these 3 different random points. And here's sort of what the explanation looks like. So have a new solution, initialized as such, and you call these 3 functions, and you have 3 different return types. Okay. So this question got a lot of downvotes. I'm gonna give an upvote, and the reason for that is that this is kind of a trick question. This is like a very tricky question. It's not really fair, in my opinion, in terms of like what they did. Yeah. Because you might be thinking like, why would this get so many downvotes? Like this it seems really simple. It's like, well, okay, you just get the random library, and all you have to do is just generate some basically generate random numbers in a relatively straightforward way. Maybe a little bit of math to use. So if you use polar coordinates, right, then you can generate for a particular theta that they use for the angle and a particular radius, or you just generate a random radius, random theta, random angle, random radius, and you're fine. There is a problem with that. I'll get to that in a second. But that's basically the truth. It's very simple in that regard, but in reality, it's actually kind of a problem. It's not that simple. Actually, you would get it wrong if you just did that, and I'll explain why. So we'll just say x double x, y, and radius, and we're going to say, you don't really need this. Actually, yeah, there's some things we do want to initialize here, but we'll have an initializer list for x center, y center. I was really nervous about submitting this one too, because I was like, there's got to be something I'm doing wrong, but it's actually really dumb, the thing that I got wrong. So I have a random device RD. This will just generate a random sort of seed value, and then we have a this thing is a method named twister. I think it's 19937. 19337. I forget which one it is. We could look it up. If this was during an interview, we would struggle to remember what this is called exactly, but it's a what they call it, method named twister M19937. MT19937. Okay. It's 2 9s. Generator. So this is a pseudo random number generator. This kind of basically gets a random number from the hardware, more or less, or that's the idea. And you use the random device to seed the random number generator, and the random number generator is used to generate numbers for your int distributions. So you'll have a standard uniform. In this case, we're going to use a real distribution of a double, and we're going to call this our distribution. And we're just going to go ahead and say gen is going to be equal to MT19937 initialized with our random device, which we call once. And then we use our distribution is going to be standard uniform real distribution object double. Yeah, double, and we're going to use, this is actually going to be from 0 to 0.0 to 1.0, and we also need to do the next after, it's called. So I think it's in the last math library, yeah, C math. So we're going to say double B, yeah, we'll call it B. It's going to be standard next after of 1.0 to standard numeric limits of double max. I think that's what you do. Right. Yeah. And we're going to use that instead. And that's our distribution. We have a generator, we have a double, we have a distribution. And so we got a random point, we're going to say, okay, we want random angle. It's going to be, oh, yeah, we also need pi. That's another thing here. Right. We can do, yeah, so we'll do pi equals, it's going to be standard arc cosine of 1. Yeah, arc cosine of -1 is pi, right? So we need pi also, and we want 2 distributions. Yeah, okay. Let's just distribute 1, dist 1, dist 2. That's fine. Dist 1 and dist 2 is going to use pi, 0.1 to 2 times pi. Actually, it's 2 pi, yeah. So that's the angle is going to be from 0 to 2 pi. Okay. So random angle is going to be dist 2 of gen. And random radius. Now this is where things get tricky. You're going to say dist 1 of gen, and you're actually going to take the square root of this, and I'll explain why in a moment, and you're going to multiply by that by your r, by your radius. And now you're going to say return this vector with x plus rand angle times r, and it's actually going to be rand angle, it's going to be standard, the sine is the x coordinate, so cosine of this random angle, and y plus the sine of this random angle times r. And I'll explain why this is in a moment. Hopefully this compiles. Next after, where is that? Yeah, it's there. From to. C math, next after. Oh, for double. Okay. Next toward. No, it's next after. Double, double. There it is. What? What? Oh. This is actually a function. So I actually have to call the function to get the max. Okay. And our test case, we're just going to change this test case slightly. Excuse me, to use a whole lot of these random points. And I'll explain in a second why we're doing that. Do a whole lot of these. Do that a few times. We have 30,000 of these calls are gonna be made. So we're gonna get a whole bunch. We really don't need that many to get what we're looking for, but just to show you something. Length of method should be the same as length of parameters. What? Do we have too many? Oh no! Oh yeah, okay. Oh. I don't know how many of these we just made. Can we count? I'm gonna quickly count how many of these there are. Write a quick script. Here, let's do that. Can we write a quick script? We're ready for this. We're gonna write a C++ program to count. Well, let's do this. Just do touch TT, MTT, insert, paste. Whoa, there's so many. Okay. All right. Now what we're gonna do is we're gonna tr. We're gonna count the number of lines in TT. 1. Okay. Now if we tr for each comma, right? We're gonna replace that with a new line character in order to count. It's taking a while. I'll do it that way. See what we get. Oh man. Oh boy, it's taking some time. How can we count the number of... Oh wow. Count the number of times a character occurred. Count the occurrences in a file. I think we have to subtract 1, I think, too, because we want to count how many there are, and then we want to oh man, that's taking a while. Whoa. Uh-oh. Something go wrong? Maybe I broke it. Oh, I know what it is. That's what's wrong. I was gonna say something's taking a while. I don't think it takes that long. Yeah, I was gonna say that took a really long time. I was waiting like 30 seconds, 40 seconds. 4,087. Okay. If we TT, oops. G, Shift G. So yeah, so it should be every line has a. I think we got it right. It should be 4,000. I think we did it correctly. So 4,087. So now we want 4,087 times to print. Want to modify our. Want to print this 4,087 times. So how do we do that? Do that from the console. Let's see if we can do this. So let's write a small program. Vim print CPP IOStream. I can also make the default size for this to be pretty large. All right, we'll use C++ to do this. Yeah, I have an idea. Yeah, okay. Standard cout. It's gonna be super simple. Well, let's do it this way. String s. No, let's just print out. Let's just print it out. So for int I0 I. You can actually use awk for this too. You don't even need a C++ program. that's not right C++ program. Let's use awk. Awk, right? Say for I equals 0, I is less than 4087, plus plus I. We're going to say S plus equals this guy, string. And then we're going to say end print S. Ready for this? Oh. And we're going to echo 0. Okay. Begin, maybe? Yeah, that's what I need to do. Why does this feel wrong? Oh, you know what? Maybe just S. There, that's what's got to be. There we go. Okay, got it. There we go. And then put that in a file. Yeah. Well, actually, we can just do it that way. Now, you know what? We'll put it in a file. Temp. Okay. Now we can open temp, and we can yank it. Now the problem with this is I gotta copy all this from somewhere, or yeah, I gotta copy it with my cursor, but I can't just scroll through the whole thing. How do I want to get it to Notepad, basically. Can we do this? Oops. How about that? I like that. That's fun. There we go. Now we can copy paste. There we go. That's how we do it. That's what we want to do. Something like that. Something like that. That was a little complicated, but I think we got there. Did we use? No, we only used shell scripts to get the. There we go. Sweet. So I think it's right. Let's give it a submit and see where we go. I'll explain everything here. So, oh no! Oh, we're wrong! Oh no! What? How is it? What? Oh no. I should have tested. Okay. So bad at this. Notice how I got every submission wrong. I haven't gotten a correct submission yet. That's great. That's pretty funny. So, all right. We should have tested. I didn't test. I'm dumb. 100, 1,000, negative 100. Okay. And I completely forgot. Oh, yeah. Oh, somewhere in the middle here. A few things I wanted to say. Oh. Yeah, okay. Does this work? There's a bunch of things I need to say. I'll just get to that in a second. Invalid test case. Nice. Nice. 1, 2, 3. And then somewhere down here is alrighty. So the things I want to describe. What is this answer? Why is it wrong? We'll fix that in a second. What did I do with these shell scripts? So the shell scripts, right, all I did was I took all the commas converted them to new line characters and counted all the new line characters. That's what I did for the shell scripts. That's how I figured out how many random point instances we created. And then to generate all of the text, I used an awk script, and I gave it one line to operate on, and in the awk script, on every line it ran this routine it was only one line, so it ran the whole routine once, and it had a variable that was a string, and it concatenated to that string in a for loop 4,087 times, which is the number we got came from our other bash shell script, and then printed that, and then I piped that output into a file. Excuse me. So all that printout was in a file, and then I opened it up with Notepad, where you can Control A to copy all of the whole file, and then I was able to copy that into this window. But this is really weird. This actually should be correct. This answer. I don't know why the submission's wrong on this input for some reason. Maybe I needed more points then. Maybe that's the problem. So let me actually do that. So we're actually gonna get a little crazy here. Going to get a little bit crazy here. So we're gonna I think we closed the window already. We're going to take this. So rand point, solution rand point. We're gonna rand point. We're gonna do 25,000 times. Echo awk for int I, or just I equals 0, I is less than 25, 1, 2, 3, plus plus I. We're going to say S equals S rand point, comma. Yeah, we gotta actually use these, escape these. And comma. Yeah, it looks like that. And then at the end, we're going to print S. Okay. There's one more here. Okay. That we're going to go into temp, vim temp. At the front of it, actually we can notepad temp. And we want to type in here, I don't know, solution. Oh, you know what? Actually, kind of want to do it this way. Vim temp. In the front, we're going to add solution, and then write it, and then we're going to notepad.exe temp, and then we're going to copy paste. And that's got to have a few changes, but we're going to do opening and closing brackets, and now we're going to have our, so it's 25,000 of those rand values, and then we're going to close this. Proof temp. Now we're going to do the same script, except for rand point, we're going to do these guys, and these we don't actually need the comma, the apostrophes, I think they're called. They're double quotes. We don't need the double quotes. Okay, the same thing. Temp, that's fine. And we're going to notepad.exe temp. Oops. Copy. But here we have something we're going to put inside in the front there. Oops, I did that wrong. Yeah, I should have. I probably should. Yeah, I should actually modify it here first. So we want an extra piece, and we want 3 things, and we could use their because they're suggesting that we're having issues with this, so we could do that. Okay, and then go to the bottom, and this should be like so. And now we can copy this. Oops. Okay. So now we get really gigantic test cases relatively quickly. That's kind of what we were going for. Now we should see something interesting here. How much time we have? Yeah, 25 minutes. Okay. So let's see what happens. Okay, wrong answer. Alrighty. So we need to figure out what we did wrong. We'll get to that in a moment. That's a little weird. I think this is supposed to be the correct answer, so I don't know why this is wrong. Oh, I know it's wrong. I know we did wrong. I take it back. I do not know exactly what we did wrong. I know we did wrong. I think I know we did wrong. Is this what we did wrong? I think I know what we did wrong. Let's just try to figure now. Alright. Well, I want to find out what we did wrong first before I explain the answer. But I don't think I've submitted a correct answer yet. That's interesting. No kidding. Wow. Really? This, I think, is supposed to be the right answer, though, which is a little weird. So, the reason why you take the square root of, you take a number from 0 to 1, a random number from 0 to 1, and you take the square root of it and then multiply by the radius. The reason you do that is because, think of a circle, right? Because you're getting points in the circle, the points that are furthest out of the circle, because there's more area of points that have, let's say if you made the circle like half radius, everything within the circle that has half the radius, and everything between the circle has half the radius, and the whole radius, right? All those points. There are way more points in the wider circle, or it's not really a wider circle, it's more like a donut, right? There's way more points in the donut than there are in the whole of the donut. Actually, you can compute exactly what it is. So if it's pi r squared is the total area, and half the radius is 1/4 pi r squared, right? You can just substitute of a fourth of the radius where the radius would be. So that means that 3/4 of the points are in the donut and 1/4 of the points are in the whole of the donut. So the way to ameliorate this is actually take the square root of your generated value, and so there will be way more points. I think it's the square root. Take the square root of your random number, and so there will be way more points in the donut than there are in the, and actually that's the relationship. It's a square root relationship. So there's a squared number of points in the donut than there would be in the whole of the donut. Is that right? Yeah, I think so. Well, it's 3 times 3/4, right? But I guess that relationship of like how does the probability of points, what's the probability that a point will be in less than or equal to a particular radius, is actually the square root of the uniform distribution. That's the square root of the radius, I guess. Maybe the over the. I don't know how to express it. I'm sorry. That's not making sense. It's the. See, this is a tricky question. Like I was kind of struggling with this. This is why I kind of wanted to go over this. Even though I kind of know the answer already, it's like hard to express. I don't fully understand it, the explanation. I kind of get it, but I don't fully get it. There's another way to express this that I do understand a little bit better, but it's still, actually, it's not really better understood. It's just a different way to express this, but it's basically, instead of using square root of 0 to 1, you can use a distribution. You can use what's called a beta distribution to give you sort of a random variable, a squared random variable. But yeah, it's basically it, is that this random variable, it's actually squared, or it's the square root of this uniform distribution instead of the, from 0 to 1 also, instead of just like a random number from 0 to the radius. Because if you did it that way, you'd have way too many points that are in the donut. So yeah, but we're having a problem here. For some reason, we're getting the wrong answer, which is a little bit strange. I wouldn't have expected that. I think the angle should be fine. The angle should be the same. Oh, it's not times the radius. Oh, that's why. That's why. That's my mistake. I'm sorry. Yeah, I was gonna say I know I did something wrong. I thought maybe I did something wrong with this part, this calculation. I didn't even use the random radius. It's always good. It's always good. There we go. That should be the right answer now. But yeah, it seems weird because you might think that you don't need to square root this. That's kind of the trick. That's why I was saying this is a trick question. You might think you don't need to square root this, but you get the wrong answer if you did that. By the way, you probably don't actually need to use the next after, but we'll do that anyway. Yeah, so if you don't square root, that's what happens. You can square root. If you do square root, then you'll get the correct answer. So, yeah, I got the wrong answer 4 times. Obviously, I tried this already a week ago, more than a week ago. Pretty interesting question. I like this question a lot. It's definitely got me thinking. It's not a. I don't want to say it's not a good question. It's like, it's kind of a difficult question, I guess. But yeah, so also you can do, and I wonder, can you do this as like a static variable? You can kind of do this as like a const expression up here. So this is more of an issue, a question about compilation. Let me see. Compiler, yeah. Static. Must be initialized by a constant expression. Oh no. Must be initialized out of line. Yeah, that's something that always kind of bothered me. A non-const static data member. Yeah, so it's so confusing about this. Oh, well, you can make it const instead of a const expression, I think. It's a little bit different. Const and const expression are not. Yeah, you can make it const. which is interesting. But if it's a const expression, wait. In-class initializer for static data member of type const double requires const expression specifier. Add const expression. No, but if you add const expression, this isn't a const expression, so it, yeah. Because you have to call a function. So right, that's something that's kind of funky with static variables that you want to initialize. Yeah, it's a very unusual thing. So actually what you need to do is before you have the solution, you actually say solution pi equals standard arc cosine, which is a little weird. It's a little weird. I don't like doing this. Type specifier for all declarations. But this is not a declaration. And this actually becomes public now, actually. Or it's a private static, which means can you put this in the class declaration itself? I don't think so. No, you can't. That has to be, it's private. Can you do this to the public member? I actually don't know if that's the problem. I don't know. Yeah, see, I've run into this issue before in the past where it's like a pain in the neck to try to get a static constant into a class where it's not a const expression that you're trying to use. It's not a declaration, that's the thing. Yeah, really interesting. Kind of weird, a little weird. Yeah, so it's kind of a weird thing. You can do something like this though. If you have static double pi, and then you say, you could say, I guess it's equal to 0 maybe, right? Can you do that? I don't think you can. Yeah, it needs to be initialized out of line. So pi, and we're going to say, we can say pi equals this. Whoops. Right? But the problem with that, excuse me, actually, this really shouldn't be that big of a deal. Sorry, I'm trying to speed up this calculation for this problem. Undefined symbol pi, solution pi. LLDR. Just breaks. Alright, we don't have to get that crazy. Yeah, that's what I'm saying. It just gets a little bit to be a bit of a problem. That's okay. We're only calling this once per execution, so it really shouldn't be that big of a deal. I'm trying to avoid using that. I'm trying to just use this once, but that's alright. Like I said, that's too much. That could be too much. I think it's too much for these kinds of problems. The what do they call that? The excuse me. The LeetCode questions, LeetCode problems. Okay, so what I want to do is actually, it's not a big deal. I think that this solution doesn't get called too often. But what is a big deal is calling this square root for every random point. Now that I want to address. So that's what we're going to look at right now. So as it turns out, as I said, the issue is that a circle, the probability of a point being less than a particular radius is actually a square root curve, not a of a random point. The probability that a random point is less than a particular radius, it's actually not. It's quadratically proportional to the it's quadratically proportional to the radius in question, not linearly, right? So because as you increase the radius, you increase the area in a square by proportionally quadratically, right? Which means that the number of points that are less than that radius increases quadratically as well in a circle. And so the probability that a point will be less than a particular radius increases quadratically, which is to say the inverse of that would be you have to take the square root. Yeah, that probability increases as you increase the radius in a quadratic way. So I don't know why you need to take the square root of this random variable from 0 to 1. I'm trying to understand it. I don't quite get it. Oh, I think I know why. Yeah, I get it. So, okay. So this is it. This is why. This is it. I get it. I get it now. I get it. Okay. Here's the reason. Because the area of points increases quadratically as you increase the radius, that means that the probability of any given point that's in a particular circle with a radius of any particular radius, let's call it R0, the probability that point is going to be contained within that radius R0 is that probability, or excuse me, the probability that you would select that point is sort of one out of the total number of points, which is proportional to the radius, right? Proportional to the radius squared. It's proportional to the area. As you increase that area, now that probability becomes 1 over that larger radius squared, and so that probability actually decreases as you increase the radius. Probability that you would have selected the point within that spot, right, or any given spot. If you sort of hold that constant, that'll decrease, and it'll decrease in an inversely proportional. Well, see, that's interesting. Like it's not 1 over the square r squared. 1 over r squared is not the same thing as square root. So that's why I'm so confused. It's so confusing. It's like, why do we just take the square root of this? Why does that work? It doesn't make sense to me. I don't get it. I don't get it. For some reason, this is how you do it, but I don't get it at all. Not at all well understood to me. I don't know. Square root of this random variable. Huh. Somehow the area being squared as the circle increases in radius causes this to require you to take the square root of this distribution of the number, the random variable, random values from this distribution from 0 to 1. Why? Not obvious at all to me. Not at all obvious to me, but that seems to be the case. It's very interesting. So, we'll just keep thinking. So, um, area increases quadratically, and so the probability that a given point is going to be in a particular sort of circle, if we had sort of these concentric circles set up, I guess the idea is like what's the probability of having radius A compared to probability of radius B, where B is greater than A, right? The R sub A and R sub B, where R sub B is larger than A. Since the circumference is pi d, which is so you'd have, that's so confusing. Sorry, I'm just thinking about it. No, that's not really the way to look at it, I think. I think you need to have that any particular radius that R sub B, the probability of choosing that radius compared to R sub A should be the square of the difference. Is that right? Well, what are those probabilities? It would be it's more like the probability of picking a point greater than some radius and the probability of picking a point less than that radius. You compare those numbers. The probability of picking something larger would be pi r squared, r, I guess, total squared minus pi r, where r is our radius we selected, r squared, which is just pi times the difference between these two squares. And that's the probability of selecting a point with a radius that's larger than r. And then the probability of selecting a radius that's less than r is pi r squared. And then that whole thing is all over pi r total squared, right? So it looks something like this. Like this is the probability of picking a point. So you have pi r squared RT minus pi r squared over pi r squared. And this is the probability of picking a point in the larger portion, and this is over t, and then this is the smaller portion Yeah. So the probability of picking a point that's less than some radius r is r over rt squared. And then the probability of picking something that's sort of in between, that's larger than r but less than t, is 1 minus pi r squared over, well, it's really, yeah, which is 1 minus r over rt squared. Excuse me. And if RT is 1, this is just r squared, right? Probability of picking some value less than r is r squared. Or less than or equal to r is r squared. Where r is, less between 0 and RT. Which means, right, so which means that when you're selecting a radius, the number of points that should have that particular radius should be the square root of 0 to 1 times r. Should show up a square root number of times rather than a uniform number of times. Yeah, that's super, like, nuanced, I guess. Like, it's hard to express that, hard to explain that. But basically, because the probability is, you want the inverse of a square root to correctly calculate the number of times, or correctly express the number of times that the points of a particular radius will actually show up when you're to get the correct distribution of points with a particular radius, you have square as many points the larger the radius, which is to say that you take the square root of your random number from 0 to 1 times r and scale it by r. But yeah, you could just do 0 to 1. So because the probability grows proportionally with the square of the radius, the probability that you'll select that particular radius, and that means you need to take the square root. It's so confusing. It's so confusing. I don't get it. I don't know how to properly express it. I don't know how to properly express it. I'm struggling. The probability that any point will be less than or equal to a particular radius is r squared. We got that, right? Where r of t is from 0 to 1. But we're really talking about the distribution, right? We're saying for any concentric circle, right? The area increases with the square of the radius. So the number of points with a particular given radius, the probability that a random point will have a particular radius increases with the square of the radius. It's proportional to the square of the radius. So that means the probability, yeah, increase of the square of the radius, right? Um, so that means you take the square root of your random number of your uniformly distributed variable. Why would that be the case? That seems so weird. Why would you take the square root if the probability increases? Seems like you should square the number. You know, like why does that? That seems so weird. Can you just square it? Does that work? Does that compile? It's a number from 0 to 1, so it'll still be from 0 to 1 when you square it. Excuse me. How about this? What happens if you do this? Why do I feel like, excuse me, why does this feel so strange to me? Oh, it's got to be the square root. It is the square root, but why? See, explaining it's hard. That's the part I'm struggling with. It makes sense intuitively, but it doesn't really make sense in a more, I guess, rigorous way, or yeah, rigorously. It's like kind of not too obvious. Do like to hit that button a few times though. I enjoy that. How do we explain this? How do we explain this? So, because the area is increasing with r, the square of r, that means the number of points that have a particular radius is increasing with r squared. Okay. So that means that if you just take the radius from a uniform distribution from 0 to 1 and scale it by r, the probability of any of those particular points is going to be equal, right? Having the number, yeah. So the number of points with a particular radius compared to the total number of points. Okay, let's do it that way. How do we do it that way? So the number of points that have a particular radius is going to be pi d, is the circumference, right? Which is 2 pi r. And the total number of points is pi r sub t squared, right? Where r is between 0 and r sub t, right? Well, okay, but We can make r between 0 and r sub t and make r sub t 1, but we don't really necessarily want to do that. I don't know. So this gets 2r over r sub t squared. Okay, but how does that help us? Right, that's the probability of any particular radius. That's the probability that any particular point. That's the probability that any particular point lies on any particular concentric circle, right? That's smaller than r sub t, has a radius smaller than r sub t, or less than or equal to r sub t. Okay. So is that the probability that of getting a particular radius r, having a particular radius r? I think that's kind of the problem, part of the problem. I think let's say if x has some p of x equals 2r rt squared. I think that means that p of x times rt squared equals 2r. R is half of p of x times rt squared. Square root of r is well, this is getting kind of close, but this doesn't seem right either. I don't know, man. There's something wrong. There's something I'm not understanding. Like, how do we get this square root in there of this uniform distribution? I don't get it. I don't get it. I don't get it. Excuse me. Like, let's take the factor that we're multiplying by r out. Let's make r of t just 1, right? Let's make r of t just 1. Oops. Keep it simple. So just unit circle. So if unit circle, what's the probability of any particular point having a particular radius? So we said 0.1, if r is 0.1, then the probability of that radius 0.1 is, we said it's 2 pi r over r sub t, but r sub t is 1, so it's just 0.2. And then, right, we said 2 pi r over pi r sub t squared, but r sub t is 1, pi's cancel, we get 2 pi r. So any particular radius is 2r. So 0.4 is 0.8. But 1, see, that doesn't make sense though, because that means that 1 is 2. That's not correct. So that's not the correct. The number of points in the circumference. It's actually not the right way to calculate that. Clearly, you can calculate the probability that it'll be less than or equal to, so that would be the area 2 pi r squared over 2 pi r sub t squared. You could definitely take the area, and then basically that would be like some infinitesimally small radius, so if we said r sub t is 1, then these all cancel, and you just get r squared. So the probability that you're less than or equal to a particular r radius would be, so if you had 0.1, it would be 0.1 squared, which is 0.01, and then 0.2, and then 0.5, and then 0.75, etc. Oops, that's not what I wanted. Oh, that's not what I wanted. Calculator, that's what I wanted. .2 squared, I think it's 0.04. 0.25 and 0.75 is 0.562. Okay, so take the square root of 0.2. It actually makes it bigger, which is a little weird. So actually, when you take the square root, it does this funny thing where it actually increases the probabilities from 0 to 1.0. There aren't enough points with that particular radius. You actually need more points of the given radius. And the more you increase the radius, you actually have less points that you're adding, which is really weird. That's so confusing. Like, I don't know. That's what I'm trying to say. Like, I'm saying that, like, it seems like it would actually be the other way around. It would be you would take a quadratic number, like you'd have you'd square the random number from 0 to 1. You might think that, but it's actually square root, which is so strange to me. Which is so strange to me. I don't get it. I don't understand. I'm so confused. I'm so confused. Excuse me. Somehow it's the square root that you want, not r squared, but the square root. Well, the cumulative probability, I guess, makes sense, right? It's the square of that radius. It's related to the area. It's proportional to that radius. So the probability that your point will have a radius less than or equal to r is r squared, right? Assuming r is between 0 and 1, right? Inclusive. Okay. How do we reconcile that? How do we think about that? Why? So if you randomly select a number between 0 and 1, in order to achieve these probabilities, apparently you actually need to select the square root. I think the reason why you take the square root is because there's a certain inversion there where you have a random variable with the probability you have a random variable x and it's related to y squared, right? And so that means that y is the square root of x. I want to say our random variable is R. That's what we want. And our uniform distribution is related to that. So I want to say that basically this implies that, so we have uniform, so if X is a uniform distribution from 0 to 1, then R squared equals X, which is to say that R this distribution is the square root of X. That's what I want to say. I think that's where this is coming from. Again, really confusing, really confusing. But the probability that, so P of R less than or equal to 1 is R squared, right? And the probability that R is less than or equal to 1 is uniformly distributed from 0 to 1. Which is to say that R squared is uniformly distributed, which is to say that R is the square root of the uniform distribution. R is a random variable. I want to say something like that. I think that's kind of what we're going for. I don't really understand how these things relate to each other, though. I don't really get it. I'm trying to understand here. I think it is that simple, but it's like I said, it's just hard to kind of wrap your brain around. This is a cumulative probability function for R. Which is kind of like saying, so I'm trying to find probability of R equals some R sub 0, right? Then it has to be probability of R less than or equal to 1 minus the probability of R less than 1, which is the probability of R less than or equal to, or I said R sub 0, really. R0 minus the probability of R less than or equal to R minus, we'll call this delta X, delta R as the limit delta R approaches 0. Yeah, something like this, which is basically 0, actually. not exactly 0. It's like yeah, this is a kind of integral, I think, or a kind of like I want to say this is like the derivative of the cumulative function, something like that. Like the cumulative function is like some kind of integral, so this has got to be some kind of a derivative. Basically, I want to show the probability function is like a square root. That's kind of what I'm going for. Like it's hard to kind of show this. What's interesting though is that this is actually, we said it's r minus r0 squared, right? And this as delta is 0 or approaches 0 of this is r squared minus r0 minus delta r squared, which then looks like negative r0 squared minus r0 squared plus 2r0 delta r. This isn't really right either though. Because this just comes out to 0. 2r0 delta r plus delta r squared. Which is not correct, actually. It's not 0. You might think it's 0, close to 0, approaching 0. Clearly this is correct though. Pi r squared minus, it's actually pi r squared minus pi r sub 0 squared over pi r squared. No, it's actually r sub 0 over r squared. Yeah. And so if you want a probability of r equal to r sub 0, naturally that's probability of r less than or equal to r sub 0 minus r less than r0. And we're suggesting that probability of r less than r0 is equal to the limit as delta r approaches 0 of probability of r minus it's going to be, we're actually suggesting that this is, well, we're trying to say that, yes, basically just Yeah, we're suggesting that as a limit as delta r approaches 0, but that in order for this to be true, so we don't actually know what this function is. That's kind of the problem. Sort of. We need to have the integral of p r equals 0 dr is equal to p of r less than or equal to r0 from 0 to r. Which is to say that p of r r0 is equal to d dx ddr p of r r0 evaluated from 0 to r. That's what we're looking for. That's what we're looking for. Yeah, a little bit confusing. This is actually what we're saying. The cumulative probability function is the sum of all of the infinitesimal slices of probability for each sort of increasing radius. So that probability function is r less than or equal to r sub 0. We're suggesting this r equals r sub 0 is r sub 0 over r squared, which is to say that if you take that derivative, so this probability then is r0, which is ddr of r sub 0 to r is r sub 0 is a constant, right? So r sub 0 squared times ddr of r in the negative second, which is actually r sub 0 squared times negative 2 r to the negative third. It's interesting. And then we say if let r be 1, then probability that r is equal to r0 is negative 2r sub 0 squared. Which doesn't make any sense at all, by the way. No sense at all. This doesn't make sense. I'm trying so hard, man. I'm trying so hard to make sense of this. This part makes sense, but the math doesn't seem to work out. Trying to get that this is the square root of a uniform distribution. Oh, yeah. This is actually a constant, this r sub t. I actually did this wrong. It's the other way around. It's r squared over r of o. Yeah. Yeah. so confusing. The probability that a given r radius is less than or equal to some r sub 0 is r over r sub 0 squared. Does that make any sense? The probability that the radius of any given point is less than or equal to some r sub 0 really depends on what r sub 0 is, doesn't it? I want to say it's just r sub 0 squared. It's so confusing. This is so confusing. Okay, I think I understand. So, well, no, I don't understand. If you take a point from with equal probability, uniformly distributed from a circle. So take a point with equal probability from a circle. Okay, I think I understand. So the probability that any particular point has, I think it's actually just, I want to say that the probability that any particular point has a given radius is the radius squared. Oh, the radius of that point squared. Yeah. Take a random point from a circle and ask what's the probability distribution of the radius of points randomly taken from a circle. That's kind of what we're asking. Like, we're asking something kind of complicated, kind of funky. What's the probability distribution of the radius of points taken from a circle? To the unit circle. That's kind of where we're at. Also, I've scratched my face to the point where I'm bleeding. It's so itchy. It's so itchy. Smell iron. Blood smells like precious metals, or smells like metal. I have a ton of iron in my blood, which I guess is a good thing overall. Yeah. What is... You gotta formulate the question correctly. That's the problem. We want to generate the points within this circle, but we want all the points to have equal probability of being generated. Which is to say that we can generate the points using polar coordinates with a radius and, you know, sort of a sine cosine pair, and an angle. Now, for any particular angle, the points that could be generated, the radius is yeah. So here's the deal. If we generate things that way, oh man, it's so itchy. It's so itchy. literally like digging into my flesh now. I think it's a mosquito bite. That must be what it is. I've been wondering what it is on my face, because I was walking a dog a few times at night outside, or once at night, but a few times outside, and I saw there was mosquitoes around. I was trying to figure out what was on my face, and that was a mosquito bite. But anyway, so because the number of points increases proportionally with respect to the square of the radius, the probability of selecting a point with a greater radius is much higher. Excuse me. Well, the probability is not the inverse. See, that's the thing. It's not just the inverse of the square. It's actually the inverse of the square operation. Like an inverse square is divide by r squared, right? The inverse proportion, rather. It's not the inverse proportion. It's actually the square root. Invert in order to have the correct number of points show up when you're generating these radii. You need to actually take the square root of 0 to 1, of a random variable from a uniform distribution, and then multiply that by the length of the radius. Which I don't really understand. I'm not really getting it. I'm like, it's not really computing. It's like, it's very intuitive, but it also doesn't make any sense at the same time. I'm trying to come up with a way where this makes sense. I'm not getting it. I'm not getting it. Let's take a look at the probability function of a uniform variable. So u of 0 to 1 is the probability function. Let's say this is x, is called little x is the value. Little x equals so if it's uniformly distributed from 0 to 1, right? There is an equal probability. So x is between everywhere other than 0 to 1. Probability of x is 0. So 0 everywhere else. And it's going to be the probability. So it's going to be 0 otherwise. And it's going to be 1 over 1 minus 0 for x between 0 and 1. Is that right? That's what the probability function looks like. It's really 1 over x, I think. What's a uniform distribution probability function look like? I'm really spending time in this now. Yeah, I don't know, man. I was so confused. This wasn't even the part that I wanted to spend a lot of time on. What does this probability function look like? 1 over b minus a. Well, a is 0 and b is 1. It's just 1. Probability PDF. Probability density function, yeah. But if it's just 1, I'm so confused. The probability of x is 1. It's really confusing. I'm so confused. I'm so confused. Also, we can close this. Close this as well. The probability that x equals little x is 1 when x is between 0 and 1, and it's 0 otherwise. But the thing is, like, if you had, 0 to 2 of, let's say, y, probably that y equals y, excuse me, is 1 over 2. And then 0 otherwise. Which is so confusing. How can the probability be half? Well, I think because the integral of this probability, take this probability dy, it's got to be equal to 1. That's kind of the deal. P of y from 0 to y. Really, it's from a to y. Well, this should be, I guess, from 0 to y. Well, that's not quite right either. Really, from a to y would be probability that y is probably that a is less than or equal to little y. Something like this, right? And then the CDF, the cumulative distribution function, is actually this P of y equals y dy from a to b. Which is this. Which is exactly this this cumulative function here. So anything from 0 to a is just 0. That's why you have the little f and the big F. This is actually the integral of this function. Over here it's a line, it's a straight line, and then after that it just stays the same value. Pretty interesting. But it's x minus a over b minus a 0 to 1 for this, in this interval. It's 1 over b minus a, but it's not, yeah, so x minus a times this, right? That's kind of interesting. Not just x times this 1 over b minus a. Because you might try to like piecewise integrate this. That's a little bit challenging, I would say. It's kind of interesting. Yeah. So anyway, I guess, yeah, I guess that does mean though that the derivative is what you're after. I mean, it's kind of what I was saying before. There's some probability that we have. It's probably a big R. The probability of big R being less than a particular radius is, we want to find the distribution of R, big R. That probability function, we can say, well, I guess the question is, what does, if u of 0, 1, x, if we had y equals x squared, square root of y equals x, but x was uniformly distributed, right? That means that y is, I don't know, if y is the square root of something that's uniformly distributed, then y squared is uniformly distributed, which is x. That means y is the square root of x. I think that's what we're getting at. We want to say y squared, r squared. If we want r squared to be uniformly distributed, that means, yeah, so r squared being uniformly distributed means that r is the square root of x. And that's why we take the square root. And that's so confusing. That is insanely confusing. Why does that make sense though? Why that? Because I can see that, like, how do we figure out that the probability of r squared is uniformly distributed? That's kind of what I'm trying to get at. Because I want to say that since r, the probability of r is less than or equal to r, is equal to, this is the cumulative density function. The cumulative density function of this, we know, is the probability, we already know this is the radius of any given point. The probability that it's less than a particular amount, less than a particular r, is going to be pi r squared over the total. Right? Which is r over rt squared. And yeah, so that's a little bit confusing. And we know that this is 0 if r is less than or equal to 0. we know this is r over rt squared if we're between, r is between 0 and r of t, and then we know this is 1. So that's the thing. Yeah, the probability that this is less than or equal to r, it's actually 0 outside r is greater than or equal to rt. That's really confusing. The cumulative density function, I think, is this. Well, it's basically 1, I guess, after this point. I don't know. See, that's really confusing. R is greater than RT. The probability that R is greater than RT is sort of artificially 0, but if we make RT kind of like an arbitrary circle, I guess, then yeah, I guess you have an infinite number of points that are larger than R of t. That's really confusing. I don't know. I'm trying to map this back to the square root of a. Trying to figure out how does this relate. Like, I'm trying to find some kind of relationship between R and the uniform distribution. That's what I'm going for. But like, clearly, if R squared is uniformly distributed, then R is the square of the uniform distribution, right? That's fine, but I guess that's it. I guess that's really the issue, is that, excuse me, it's the area that's being uniformly distributed. So it's, if A is a uniform distribution, and A is pi r squared, which means that that's a uniform distribution. Why are we dividing by pi? Is another question. That means that r squared is 1 over pi times the uniform distribution. Okay, that doesn't make sense though. That doesn't make sense. Because there's like a pi in there, somewhere in there, that's got to be extracted or considered or what have you. No, man, this doesn't make sense either. How do I show this? I mean, it seems intuitive, but it doesn't seem to make sense. No, it doesn't make sense. It does not make sense. This makes sense. If r squared is uniformly distributed from 0 to 1, then r is the square root of 0 and 1. That's fine. That makes sense. But how do we get here? How does that happen? I guess you'd say the reason for this is, but then you have another question of like, what about this? Like some constant k. Because I thought this might be make more sense. I actually wanted to try this before. Whoops. Actually, why doesn't that work? That's a good question too. It's actually incorrect to do this. What I'm about to do. So this is dist 1, right? Just compile. Yeah. And part of the reason, by the way, is that where is part of the reason, by the way, is that this k doesn't go all the way to r squared, right? Or it doesn't go all the way to r if you take the square root of this. I guess maybe that's it. Maybe that's what it is. It's if you have this 0 to k squared, then it's equal to k squared times 0, 1, and then r is k times the square root of 0, 1. For some reason, can you do this? Oops. Actually, is that what I need to do? I think I tried that too, and that didn't work either. Does that make sense? Yeah, you wouldn't have a long enough radius if you. Oh, that's correct. No kidding. Oh. Huh. Oh wow. Okay, so that's exactly what's happening. All right. That's interesting. Yeah, well, basically, you have this random variable r, and it's going to be distributed you want it to be uniformly distributed from 0 to k squared, but it's actually r squared that you want uniformly distributed. Oh. Okay. From 0 to r to k squared. Which means that r is the square root of that uniform distribution from 0 to k squared. And the reason that's r squared and not r is because the area increases. The number of points, the area or the number of points that could have that particular r value is proportional to r squared. Yeah, rather than r. So the selection of those points is excuse me, uniformly distributed as well in that way. Huh. I mean, it's interesting. I think I understand, but I don't know how you get to here. That you have this random variable r squared that's uniformly distributed from. I think it's because of the area. Like that's what I'm thinking. Yeah, you want the radius squared to be uniformly distributed. You know what? I got it. If a is a random variable, then it's going to be pi times r squared. And that would mean you'd want this to be uniformly distributed from some constant k, where since you want every point to have equal probability of being chosen, that means that you'd want in the area, which is pi r squared, which is pi times some random variable squared, some random radius squared. You want every point that you could select within that area to have the same probability being uniformly distributed, which actually means that you would have u of 0 pi k squared, right? Which is pi of u k squared. And this is equal to pi r squared, where r is the random variable of the radius, which then gives you pi uk squared, which actually then gives you, which then leads you to r squared equals u of k squared, which is also just k squared u of 0, 1. Then gives you r as the square root k times the square root of u1. Okay, that is super confusing, but I get it now. Yeah, I get it now. Okay, I see how you get the. It's actually really simple, but it's just kind of hard to understand. Yeah, it's actually it's really what you're doing is just saying take the points, let the area every point from the area be uniformly distributed. We'll use k for the radius. So for some circle with radius k, the selection, we want to select any particular point with uniform distribution. That's actually what's going on here. And then that becomes pi k squared u of 0, 1. And then we can say the random variable for the radius is related to the random variable a by pi r squared, which is then pi k squared u of 0, 1, which then gives you r as square root of this, k square root of u1. That's actually how this was done. This is actually really simple. This is actually really simple. Now what's cool about this is, what's interesting about this is that actually what I wanted to do is you can optimize this. So r is a random number from u k squared, square root of k u k squared. Well, as it turns out, if you go on the Wikipedia, right, for continuous values. There's something interesting here. This says, I want to show you something. It's the beta function I'm looking for. The beta distribution, yeah. This is kind of neat. Watch this. This is actually what I wanted to show, but I was having such a hard time trying to figure out like the maths. That's actually really simple, the maths there, but it's distributions are kind of special, I guess. So that's why it's not the most intuitive, I guess. It's not, or not, I shouldn't say the most intuitive, but like it's. Let's just say that was, I don't know. Let's just say that was challenging for me. It's challenging me to kind of put that together. So there's something special here that I want to show about the beta function and uniform functions. Okay. You see this? Oh no. Actually, maybe I should go to this one. I did it wrong. I think it's, hold on. The beta distribution. Oh, here it is. Yeah, okay. So, if x has a standard uniform distribution, then y equals x raised to the n has a beta distribution with parameters 1 over 1, 1 over n, 1. As such, standard uniform distribution is a special case of the beta distribution with parameters 1, 1. Okay, so here's a relationship between the beta distribution and the uniform distribution. There's a relationship between gamma distribution and beta distribution. On Stack Overflow, they have an explanation. Ready for this? There's a formula. But yeah, so x over x plus y is the, if x and y are gamma distributions, then x over x plus y is a beta distribution. And actually, the gamma distributions are, I think it's alpha and beta, and that'll give you the beta gamma. If you have A and B for the gamma distributions, this is like a really neat thing. Excuse me. A gamma distribution is alpha and beta. So I think it's alpha 0 and beta 0. It goes something like this. It's, if you say A 0 is your x and B and 0b is your y, then x over x plus y is a beta distribution with A and B. So you can build your beta distribution out of two gamma distributions. Or just a gamma distribution, which The CPV reference doesn't provide a beta distribution, but it does provide a gamma distribution. And a uniform distribution is beta of 1, 1, right? And a random variable, if x is equal to y raised to the n. So the reason why I'm going through all this is because we want to optimize our program to not use the square root function when we generate random points, which means that we want to generate our random values for the radius directly from this distribution of r for r, which means we can take r to be k times the square root of u of 0, 1. So we just multiply k by r by this, and this, let's call this a or y, or well, alpha, right? Or just, I don't know, we'll call it y, is equal to the square root of u 0, 1. That means that y squared equals this u of 0, 1. And we said before that if, let's call this x, right, which is 0, 1, which is to say that y is square root of x. If this is a uniform distribution, so we go back to our, if x has a standard uniform distribution, then y equals x raised to the n. So x has a standard uniform distribution, y equals x raised to the n, has beta distribution with parameters 1 over n, 1, which means that y equals beta of 2, 1. Yeah. That's the distribution for y. And that means that r is equal to k times beta 2, 1. And then we can use our gamma distribution for, I don't know, G1, G2, we'll call it G1 would be beta, gamma of, just go lowercase g of 2, 0, and G2 is little gamma of 0, 1, and then that means that r is equal to k times big G1 over little g1. Okay, it's got real complicated, but that's what I wanted to show, is that you can optimize this, hopefully somewhat optimize this this function by, instead of using a square root, you can use a beta distribution. And actually, you can even multiply this k right in there, right? Well, I don't know if you can exactly. I think you have to still multiply by k. But yeah, so that's what I wanted to try. I wanted to see how much faster it would be if we used the beta and the gamma. I actually don't know if it would be much faster. It might be a little bit faster than using the square root function. Yeah, so that's the thing. We're going to go for 2, 1. So I want to see if this works. That's like the thing I'm going for. I just want to see if it works. So we got this correct, but we want to see if we can also do a few other approaches here. So we're going to say this random radius we want we'll do dis2, and we're going to have standard gamma distribution. If you can imagine that, using a gamma distribution. Gamma. And It's going to be D12. Okay. We're going to use double 1, 2. Yeah. So gamma distribution G1, G2, we'll say, and we're going to say okay. So we'll just say double B. Standard next after. Do a similar thing here. Okay. So we want G1 to be a gamma distribution with, it's going to be A and B. So A is 2 and B is 0, right? Or A and B, and then the other one is the other way. Oops. G2 is 0 and B again is going to be 1. Should be 1. So this is going to be 1.0, the limits max. And then this one is 0. So limits max, 0.0. Right, because these are going to be inclusive ranges or inclusive values. Now, I don't know that actually we even need to use this for the gamma distribution. 1 to 2. That's actually unneeded. Alphas and the alpha and the beta are exact, I think. Or this doesn't define an interval the way that a uniform distribution does. Oh. Okay. Yeah. So actually I don't need to use that. I don't need to use the next after either in here. Close all these too, I think. Actually I might need to keep that open. I might get it wrong, because I didn't do the math myself. All right, so we actually don't need this next after anymore either. Okay, so it's actually 2, 0, and 0, 1 are G1 and G2, if you can imagine that. Excuse me. And then, yeah, you're actually going to take the random radius is no longer a square root. It's just multiplied by r times, we get double x equals, I don't know, we'll call it A, just do A of G1 gen, B is G2 gen, and we're going to say of A over A plus B, and R times that. Yeah, there we go. Okay. Let's see what happens if we do this. Does this compile? Let's start with that. Does this compile? Did I get the math right? Compiler. Okay. Oh, it's going to be a double. And these are doubles also. And then I guess it B is double B. All right. What happens here? What happens? What do we get? Wrong answer. No. Look at his output. Nan. Just says this doesn't make any sense at all. You're wrong, friend. You are wrong. Really? That's kind of annoying. Huh. Not what I was expecting. Hmm. More chances to be the right one. Um. Really? So this doesn't have. Someone had a Stack Overflow post that showed that I don't know how. Here it is. Yes. No. Wrong. This one. This is the x over x plus y. But the problem is. So real type AB, beta distribution. Um, But what is x gamma and y gamma set to? A gamma A, B gamma B. Prim A, prim B. Yeah, it's A0, 0B for the second one. B gamma is A is alpha. Oh, excuse me. No, B is alpha. Oh, okay. So I got it wrong. That's what I was trying to find out what the parameters are for the A gamma and B gamma. I think it's, what's the default for gamma? Oh, it's just one. Beta is just one. Oh, okay. Yeah, I was missing the formula. I was missing how they combine correctly. So it's actually just, it really is just 2 and 1 then, I think. I suppose. Hey, oh, it's correct. Hey, check that out. Really? Wow, that's fun. That's fun. Check me out. All right, this is not faster though. This is not faster at all. But it is interesting. I noticed that code was heavily templated. The code that the fellow wrote of a beta distribution. I wouldn't have written it that way. Excuse me, I would have made it probably a lot less templating. Excuse me, maybe a template for the real type. But yeah, I think excuse me. Yeah, this works too. This is not faster though. It's not even remotely faster. Which is interesting. Uses more memory. Yeah, it uses about as much memory, but yeah, it's kind of interesting. Not faster. Better off just running the square root function. That's very interesting. I guess because the generator you have to call, function call. Man, all that for. But yeah, I figured there was a relationship there where you didn't actually need to use the square root function, but the square root function is about as fast. It's actually a little bit faster than having all this. Excuse me, extra machinery here. The only issue I think you have is really I think the reason why this is so slow is because of the random generator that we're using. All these classes that we're using, the random device, this MT19937 pseudo-random number generator, a uniform yield distribution that we want to use, and our gamma distribution that we want to use to avoid using the square root function. Ultimately, though, it's probably simpler to just use the square root function. So yeah, that's a lot of fun. We spent hours on this, so forgive me for that. I don't know. I thought that was gonna be faster, but it was kind of challenging for me to. It was challenging for me to figure out exactly why points being selected from the area in a uniform way would imply that the radius has to have not a slightly modified version of the uniform distribution. The math on that's actually not too bad, but it's definitely very interesting how that works out. And then you can get like really crazy with your maths and go into how do you use gamma distributions to emulate beta distributions to emulate a uniform distribution that's been square rooted, and get that distribution, generate that programmatically with C++. So that's pretty cool. That's pretty interesting. Yeah. So thank you for watching. Talk to you all soon. Have a good rest of your day. Take care. Oh, I might pick up another problem in a moment. I think I'm gonna do another problem. Yeah. Mm-hmm.